Okay, in today's video, I'm going to go over some example problems for transformers. In the previous video, I went over, which you can link to in the upper right-hand corner of this video, I went over an explanation of how transformers function, their parts, and all that kind of fun stuff. But now we're going to do some example problems using the equations and the principles we developed in the first video. And I just want to review really quick, because we have these equations we developed in the previous video. I want to point out again, remember that using this equation, and this is the equation that relates the ratio of the voltages to the number of windings, secondary and primary. And it says here that if the number of windings on the secondary coil is greater than the number of windings on the primary coil, then the voltage across the secondary coil will be greater than the voltage across the primary coil. So you want to increase, step up the voltage, which we call that a step-up transformer. Then you put more windings on the secondary coil, and you get more voltage out of the secondary coil. Again, that's a step-up transformer. You want less, you put less windings on the secondary coil. Now, for the current, it's the opposite. And you'll notice it's the opposite because here it's the ratio of the voltage is the secondary to primary. For the current, it's primary to secondary. So in this case, if you want number of windings on the secondary coil is greater than the number of windings on the primary, then the current through the secondary coil will be less than the current through the primary coil. So if you want less current, you put more windings on the secondary coil. If you put more windings on the secondary coil, you get less current. If you want more current, then you have to put less windings on the secondary coil. Okay, to me that seems a little counterintuitive. But if for the voltages more equals more, for the current, more windings is less current. Keep that in mind when we fill in these two tables. Now here you can see this is the voltage table, this is the current table. Windings, primary, secondary, voltage, primary, secondary, windings, and currents, primary, secondary. All right, now we should be able to do these without kind of like writing down the math. We should just know that if we have twice as many windings on the secondary coil, because this is 500, this is primary 250, then what is the voltage on the secondary going to be? Well, more windings here, it should be either twice as many, 240 or 60. And in this case, it's what do you think it is? 240. Now we're going to go down here. Let's do the current because we're trying to want to understand the relationship between the voltages and the current. You can see this is still 250 and 500. Now in this case, we have 1.5 amps. We have twice as many windings in the secondary. Now is this going to be 3 or 0.75? Well, more windings in the secondary equals, we just said in the previous slide, less current, half as much current. Okay, the next one is 1200 and 400. We decrease this by a factor of 3, right? 4 times 3 is 12, so we decrease it by a factor of 3 on the secondary, and that means that this is either going to be 300 or 2700. Those are really the only two options in this case. And of course, there's only one right answer, which that would be 300. Now down here, the same thing, 1200, 400. Less windings equals more current, 6. Right? We decrease the windings by a factor of 3. We increase the current by a factor of 3. Now the next two in each case are not really related to each other directly like that, but here you can see on this one we have 3 times as many windings on the secondary, and that means that the number of windings, 3 times as much voltage on the secondary, and that means the number of windings should be 3 times more or 3 times less. I think it's going to be 3 times more. Now for this one, we have a quarter of the number of windings. So that means that this voltage is going to be a quarter of what this one is. So this is 16,000. Now here we have the currents. We have 4 times as much current. So that means that it has to be 4 times as less windings. I don't think that's the right way to say it. But now this one we have 1.5. And here we have 3 times the number of windings. But we decrease the current here because we have more windings in the secondary, so that means that this has to either be 0.5 or 4.5. Okay, so that's kind of a conceptual. You should understand those relationships between the currents and the voltages and the windings. All right, now we have 3 problems we're going to do. We have an ideal transformer that has a primary coil has 750 windings. It's connected to a 230 volt source. How many windings are needed on the secondary coil to drop the voltage down, to step the voltage down to 12.5. So we want to know windings in the secondary. Now I'm going to start with this equation. This is the equation we developed in the previous video for the relationship between the voltages and the number of windings. We want to solve for the number of windings on the secondary, NS. So NS is going to be equal to VS divided by VP. times the number of windings on the primary. We can just plug those values in, 12.5 divided by 230, and that would be 750, and that means we're going to have 41. We want to have less voltage, so we want to have less windings. Okay, that was just about like 40.6. I rounded it to 41. Okay, the next one, we have a secondary coil, has an ideal transformer. It has 2150 turns. Turns, windings, same thing, coils. If the primary coil is 900 and there's a current of 2.15, what would be the current through the secondary coil? Now you can see we have more windings on the secondary than on the primary. So we should be thinking, well, is it going to be more or less? Okay, more than less than 2.15. More windings on the secondary should be less current. Okay, so this is the equation we're going to use. We showed this equation in the previous video and on the first two slides, or the first slide, and we plug the values in. We get 900 divided by 2150 times 2.15, and we get 0.9 amperes. And just like I said, more windings on the secondary than on the primary equals lower current than what we started out with. Okay, primary was 2.15, the secondary current is 0.9. Okay, now this one kind of has three parts to it. We'll go through it relatively nicely. We have an ideal 600 watt transformer. It has 100 windings on the primary and 200 on the secondary. And we want to know, first of all, is this a step up or a step down? Is it going to step the voltage up or step the voltage down? We have more windings on the secondary than we have on the primary. So we have more windings on the secondary, and that means it's going to step the voltage up. Well, let's calculate what will the voltage be. Okay, the blah, blah, blah. It says here that it's when it's connected to a 240 volt source, what will the output voltage be? So we have twice as many windings on the secondary than the primary. So you should be able to think like ahead of time, what will it be? Okay, well, we're just going to use the equation we had from the beginning of the video, and we multiply, first we divide 200 by 100, and we get 2 times 120 is 240. And we have twice as many windings. The input voltage was 120, and that means the output or the secondary voltage should be 240. All right. Now we're going to get, I guess, the currents. We did the voltage already. We got that. That's what this is right here. We want to get the currents. Now the current, we have to use the power equation, okay, because we don't have enough information. We don't have any of the currents at all. So we're going to use the power equation, the power primary, current primary, and voltage primary, and we solve for the current, and that means it's the power primary, and this is the primary was the 600 watts, divided by the voltage, okay, and that's 5 amps. Now, the power on the secondary is the same. Okay, that's if we have an ideal transformer, then the power should be the same. So we can use this equation, and we have power secondary, which is the same because they're the same. Energy in is energy out, and we have the voltage on the secondary. Now, let's see, we have twice as many windings on the secondary, so this should be either 10 or maybe 2.5. So there you go. Okay, I think we did like 3, maybe 4 problems, considering that was a couple parts there. And for the practicing for calculations for transformers, I hope you found the video helpful. If you did, please do all the following 4 things. Subscribe to my channel, get all my excellent physics, chemistry, and math videos. Give me a thumbs up for this video. Leave me a nice positive comment in the comment section below. And don't forget, once again, sharing is caring. Share this video with all of your friends. Show them just how much you care. Thanks for watching. We'll see you in the next video.